All right, reinforcement learning. It's an important part of many of the recent exciting advancements that you've heard about in machine learning, but it's also a bit of a new way to look at the problem, and it feels very different than what we've been studying for the majority of this course, which is supervised learning. There's a whole bunch of other things about having an agent interact with an environment. They have different names for what training examples are. Things don't all quite mean, and it's a little bit of a little discordant. I personally struggle with it when I go through it, and this lecture is intended to give you an introduction to this other way of thinking about machine learning that is actually quite important and which I strongly believe will be as important or even more important 10 years from now than it is today. So let's get started. Reinforcement learning. It's, as I said, a little bit of a different thought process. You're learning to interact with an environment. So you can imagine that you are trying to teach a robot how to move through a room or move through a world or accomplish something. You're trying to teach a computer how to win an open-ended game where it's not really clear how you and the other player are going to interact. You could teach a computer how to control an industrial plant where there's all sorts of processes and temperatures and timings, and they can affect each other in odd ways. There's also recently been work on using reinforcement learning to do the hyperparameter tuning process that we've spent so much time on, like looking at sweeps and interpreting what to try based on that. All of these are good places to use reinforcement learning, and they're also places where standard supervised learning classification, it's kind of hard to figure out how to set up, well, what is a training example for a robot in the world who's trying to accomplish a task that takes 20 minutes? You know, what do I do right now to accomplish that thing way in the future? What is the training example? Reinforcement learning, the idea is to do this with as little human training as possible, keep the human out of the loop and just let the agent explore the environment. And as I said, it's like at each particular step of a reinforcement learning process, it might not be obvious to a human or to an expert or to, anyone. Well, what should this agent do right now to accomplish that goal? So to be a little bit more concrete, in supervised learning, remember we talked about the goal is to learn this f of x equals y, where x is the training sample and y is the label or the features and the label that you're trying to predict. In reinforcement learning, the goal is a little bit different. The goal is to maximize over all time the reward that the agent gets for taking action I in state I. So taking the action it took at time I in the state that it was in at time I. Somehow you get this notion of a reward, and you want to learn an agent that is good at getting rewards over time. And if you break this down a little bit, compare these two, you could say that this thing here is the X, for example. You might think of it this way, like what the state of the world, like what's in that message you just received, what are the demographics of that person, what's in the image of the eye you're trying to look at. The action could maybe be like, well, what do you do? What's the why? And then the reward is, well, maybe that's actually the why. So, okay, things are a little bit similar, but a little bit different. Let's go on and get into the examples a little bit further. And the way you get data for your reinforcement learning process is that you do interactions. And that is the agent at any time will be in a particular state. The agent can try taking any action the agent wants to try, and then the data is returning to the agent, well, here's the reward you got, and here's the state you ended up in. And if you have an environment that you can represent like this, and we'll get into a little bit of the specifics of what exactly technically you need to have this representation that will work. Well, if you have this kind of environment, there are reinforcement learning algorithms where you can just say, hey, agent, go figure it out. Go learn how to maximize that. And in this lecture, we're going to go through very, very, very early simple version of that, and maybe one sample of how to get a little bit more complex. But of course, reinforcement learning is a big field with a lot of excitement in it, and there's no way you're going to learn state-of-the-art stuff in 1 2-hour lecture, or however long this lecture ends up being. My wife always says, so my wife has been editing these, and she always says, oh yeah, anytime you say a time, you're like, oh, it's going to be 20 minutes, and you end up talking for an hour. So this time I overshot. It's not going to be 2 hours. It'll be somewhere in between. I'm sure she's going to cut that out. Another way to think of reinforcement learning is that here you have the agent and the environment that the agent is trying to interact with. And the agent will take an action and sort of send that action and say, here's what I'm doing, Mr. Environment. And the environment will say, well, here's your new state, and here's your reward, Mrs. Agent. It's a simple way to think of it. And then the agent can continue to interact with the environment over time and just iterate this process on and on and on. Now, what are some successes of reinforcement learning? An early one, which I believe is talked about in the book, is this learning how to play backgammon. 1995 reinforcement learning. And here the goal is you could look at a backgammon board and you could say, well, this is the position of all the pieces. What am I going to try to do? Well, let's predict the probability I'm going to win based on that's the position of all the pieces. I don't know how you're going to get a label for that, right? And I mean, an expert looks at this and says, well, I think it's about a 22% chance black's going to, I don't know. But you could set this up as a reinforcement learning problem where the state is the board. So that's the state of the environment, is where all the pieces are on the board. The actions are every valid move that you could take. And the reward is win or lose. And now this reward is something that's a little bit hard to understand for someone with their brain wired the way my brain ended up getting wired, kind of coming up through the supervised learning, kind of more traditional machine learning approach, is that the reward is not like a label. Because at any particular state, you don't know. I mean, you don't even know what the answer to this is. You're getting like zero reward signal until the very end of the game. And so a big challenge in reinforcement learning is trying to fit that state and reward up so that you can get enough signal early enough so you can start to learn. Kind of like we were talking about residual nets. How do you get that reward from the end of the network back to the beginning of the network so you can start to learn? It's a similar type of challenge in reinforcement learning. We'll see more and more what I mean when I say that. To do this with reinforcement learning, they used a neural network with 80 hidden units. 80 hidden units. Can you imagine? How many were in the things we talked about last week? Initialized to random weights, like of course you would do. Then you would select a move based on the network and a shallow search of like, well, if I take that move and they take their move and I take my move, where do we end up? Instead of using the prediction of the network on this move, you would use the prediction of the network 4 moves in the future, assuming everyone played sort of optimally. And then you just learn by playing against yourself. 1.5 million games playing against itself, and this process is competitive with world-class players. Now, I haven't talked through what the algorithm is that they did beyond, the structure of the model or how they turn this into training examples. We're gonna see that. We'll see a few approaches to that throughout the course of this lecture. Just to give a sense, 1.5 million games, very simple network, sort of complicated game. I mean, I don't know, it's not the hardest game in the universe, but a long time ago, competitive with world-class players. Interesting result. Another very interesting result is this Atari 2600 games learner using reinforcement learning. And the cool thing about it is that they could use the same model and parameter on 50 classic Atari games. In this case, instead of taking the board as input, they took the raw pixels of what the Atari would render on the screen as the state. The state is what you see there. So there's computer vision baked into this reinforcement learning problem. The actions are the valid actions that you can take in an Atari game, and it's kind of simple. I think there was 1 button and 4 directions, maybe combination direction, something along those lines. So the action space is pretty small. The state space is pretty gigantic because the pixels could be anything. And then the reward is the game score, whatever the game score happens to be. Maybe they wrote some custom logic to extract the game score from the image or somehow feed that signal to the reinforcement learning. They didn't make it OCR to figure out if it's winning or losing. But okay, that's the setup for it. And then here is 50 Atari games. And this line here, everything below this line indicates that the system was unable to learn better than human level play. And everything above this line indicates that the system is crushing humans. And I don't know if these were who's a world-class Atari crawl player today? I mean, humans haven't necessarily dedicated themselves to that for many, many years, but just the point is that take an average human, let them play the game for a while. How good do they get? Well, this algorithm is able to totally crush many, many humans at many, many games. But then there's these games at the bottom where the algorithm pretty much failed. Very, very difficult to make progress and succeed. And we'll see a little bit about the properties of a problem that make it difficult for reinforcement learning. This one that it's the worst at, Montezuma's Revenge, it's a very, very difficult game to get any reward in that you have to overcome multiple challenges before you get any signal like, hey, you're heading in the right direction. So raw reinforcement learning has a hard time with that. Now, people have since come up with tweaks and other ways to encode information to get past this. But the fundamental challenge, I think, if you look at the very first level, it's a platformer where there's like a ladder, maybe another ladder, something like that. And then there's a key. I think the key's on this side. And the player has to jump there, jump over a snake, climb down the ladder, go over there, go up, go over, go up, pick up the key, go all the way back, redo all that, jump over there and unlock the door. That's a complicated set of steps to get any reward of like, yes, you've scored a point for leaving the level. Anyway, this is sort of a long-winded way of saying that this property of rewards that are way too delayed, state spaces that are way too large, action spaces that are way too large, makes it difficult for reinforcement learning. But when things line up and you can set up the problem well, reinforcement learning can be totally, totally awesome. And modern work can improve on this. Another thing that is very interesting is this robotics. So here's a state space was the joints of these robots and the velocities that each limb is moving at, accelerometers, and then the terrain. I think they gave it a little representation of what the terrain looks like. It wasn't full computer vision. I think it was like bottom 20% is obscured or the top 10% is obscured. The actions are just apply torques, just do the robotics things, apply, move this joint in the up direction. And then the rewards involved how quickly the robot was moving. And I say this minus stuff thing because there was a negative reward for leaving the center or something like that. I don't remember exactly what it was, but they did a little bit of what's called reward shaping. We'll talk about that more as this lecture goes on to help the robot achieve the task. Anyway, it's pretty cool. You just learn to run with absolutely no human input other than setting up this environment and a simulator and hooking the agent and the environment together. Here's another one of a spider learning to run and jump. Oh, it died. And then here's another one. This is like the disco hand. In this case, they taught a humanoid robot to walk, and then they started messing with the floor. And so this robot has never actually been trained to move on a messed up floor like this where everything's rocking and shaking, but it somehow figures out how to do it. And I guess to keep balance, I don't know, maybe it just got to work on its dance moves. Another big success of reinforcement learning is AlphaGo, and this has gone on to turn into, these guys have been working on StarCraft 2. And I think you might argue that between AlphaGo and StarCraft 2, they are two of the largest state space, most actively competitive human games in existence. And so the question is, can we, with very limited feature engineering, just algorithm and connecting agents and things, can we teach a computer to learn how to win at these highly competitive games against humans who are experts? And top StarCraft players make like $600,000. That's their yearly earnings, something like that. It is a very competitive. A lot of people do that a lot. Can we learn how to beat humans at these hard games where search alone is just totally like, search isn't going to work. The state space is too big. You'll never win by just searching for possible moves, sort of like what happened with chess. And just very, very simple. State is the board space, actions are the valid moves, and the reward is at the end of the game. You played a 45-minute StarCraft game. Did you win or lose? You get a reward or you don't get a reward. No indication of any particular intermediate state. Is this a good thing to do? Is that a good thing to do? No. Reinforcement learning has to figure that out on its own. This chart shows the hours of training time that they spent on the reinforcement learning algorithm versus supervised learning by taking labels from expert humans games. Then this is the number of training hours of either the computer playing against itself or the computer building a model on human. And this axis, ELO, is a common thing. I think it might have come from chess. It's very common in online games where you get matched to people based on your ELO ratings, and whoever wins, their ELO goes up, and whoever loses, their ELO goes down. So it's a ranking system where the best players will percolate to the top. And at the highlight, like this is a, I guess, gigantic gap in terms of ability. And we'll see that in a second, just how gigantic these gaps can get quickly in ELO. A slightly advanced version of the algorithm called AlphaGo 0, and by 0, it takes absolutely no bootstrapping. I believe this version, they had some bootstrapping by training on a limited number of humans, something like that, just to get it started towards ever getting rewards. Then another version of it, AlphaGo 0, that doesn't do that. Training time is now in days instead of in hours. Interesting thing here, this green line is the AlphaGo that beat the world human Go champion. That's the same as this blue line right there. Beat the world champion. And okay, something I forgot to say when we were talking over here, you could see that with the supervised learning algorithm, which is taking samples from the human, they weren't able to ever beat the version of the system that can beat the humans. And I don't know that that's intrinsically, like, you're not going to prove that you couldn't supervised learn something to beat the best human in the world. It is just interesting that reinforcement learning in a relatively low amount of time is able to beat humans, whereas supervised learning maybe starts to asymptote. The point I'm trying to make is, here's the version of the algorithm that beat a human with 4 or 5 days and 0 input knowledge. They're able to train a system that can beat that version of their Go game. So starting from scratch, a game as complicated as Go, boom, 4 or 5 days, you're beating master level humans. That's crazy. And you could say, well, okay, Go, well, let's apply the same algorithm to any other human endeavor, like fighter pilots or chefs or whatever you want to do. I mean, maybe the action space is a little bit too large in those systems for this algorithm to apply directly, but you're talking about, wow, human level performance in 4 or 5 days, assuming you have the right setup of a fast simulator where you're able to try things, get feedback, etc., etc. Then they run it for a little amount of time, and they've improved the ELO from like 3,500 to maybe getting up to 4,000. And this version of the algorithm beat this version of the algorithm 100 to 0. Just gives you a sense of how much skill is represented by each increment of ELO. Then in this particular experiment, they ran it out to 40 some days, and looks like it asymptoted a little there, but then it started improving some more there. It looks like maybe they got bored, maybe they could run it further. But after 40 days with very little prior knowledge, very little feature engineering, this algorithm is beating things that beat the best human in the world 100 to 0, and made all this additional progress past that point. Pretty amazing. They applied the same algorithm back to chess, and instead of like the 63 hours, from start to finish in 24 hours, it was able to learn how to outplay humans, beat like human grandmasters at chess. Or maybe I'm not exactly sure if it's grandmasters, but like these games, they're sort of solved. Simple observable states, relatively, gigantic but not too gigantic state spaces, sort of limited moves. They're sort of solved. Computers can beat humans at them. Now, why is reinforcement learning different than supervised learning? Highlight some of the properties. Number one is this delayed rewards property. And I've made this point several times, but to just say it again, at any particular state, it's not clear whether you're doing well or you're not doing well. It may take 10 states more, 100 more actions, 200 more actions before you have any sense of like, hey, you're doing a good job. Keep going. That's very different than supervised learning, where at each step you're like, okay, here's what's going on. Here's what I need you to predict. Boop, 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 boop. Very different. Another difference is that the agent gets to choose the training data by deciding which actions to take and in which order. That is, at any particular S, the agent could do action 1, 2, 3, 4, whatever the actions they have available. It's the agent's choice. And the agent can say, well, I want to take action 1 because I want to like learn something down that path. Or it could say, I want to take action 2 because I've never tried action 2 before and I'm very interested to see what happens when I take action 2. So there's this trade-off between exploring locally, exploring in the future, exploring at all, or going and getting your reward. That's explore versus exploit is what you'll commonly hear. Another way to say is it's lifelong learning, and that the agent, even if the agent is at master level, beating humans as good as it wants to do, it always has the opportunity to say, I've never quite seen this before. I know I could get reward if I go that way, but what happens if I go this way instead? Always a trade-off that you can have in a... And then the other one is that there's very different terminology. And I admitted it right at the beginning. It's very confusing. Because like in the early days when I started talking to reinforcement learning people, I remember having these crazy conversations where they said, oh, and then blah, 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 and here's the reward. I'm like, you mean the label? They said, no, it's a reward. I'm like, it's just, why you call it a label? Why are you trying to invent your own crazy, well, you're inventing your own crazy language because of all this other stuff that goes into the difference between a label and a reward. So they are really different. And if you think of a reward as a label, and think, well, I can just apply decision trees to this. Not so much. Maybe in some limited sense, maybe that works out to be a subcomponent of what the reinforcement learning algorithms do. But if you're thinking about it that way, you're kind of missing the game. Pretty important. And that's why I want to spend this lecture on reinforcement learning, so you can build some of the mental structure to start to have these conversations with reinforcement learning people who are working on and achieving really exciting results. Now, moving on, getting a little bit more technical about what is the setup for the type of reinforcement learning we're doing. Of course, like everything, one lecture, we can't cover all the subtleties, but for the purposes of today, we're going to talk about doing reinforcement learning with respect to a Markov decision process. And so that's what the environment will be. It will be a Markov decision process. What that implies, what that means, is that we're in a discrete time stochastic control process. Let me talk it through first with drawings, then I'll click some more, and then we'll see where we get. So discrete time, that means t equals 1, 2, 3. It's not continuous, like, time is now 1.174. No, there's discrete steps, time. Stochastic control process means that you can be in a state and take an action. Now, the resulting state that you end up in is not deterministic. There is some randomness in it, that the same action in the same state multiple times may not result in the same thing. Now let me erase this and then say that again. Each time step, S, the agent chooses an action A from A sub S. Now we're going to introduce, there's kind of a lot of math in this, and there's kind of the different concepts. It's not really math, but it's formal definitions of what all these things are. So A sub S is the set of available actions you have. And then the agent moves to a new state with the probability. So that says the probability, given that you took action A, of going from state S to state S prime. That's a thing that exists. And then the agent receives a reward. And what this says is it's the reward you get for taking action A in state S and ending up moving to state S prime. So the reward itself is non-deterministic, in that the stochastic state transition probability matrix, or however you want to think about representing it, influences what reward you're going to get. We'll see examples of exactly what that means. But if you're like, if the robot's supposed to put something down and stochastically something twists and it puts it down slightly differently and the thing breaks, the robot took the most likely action, still didn't get the reward. So it's a stochastic process. And another property of Markov decision processes is that every outcome depends only on the state that the robot's in, or that whatever the agent's in, and the action it takes, and and this state transition probability, but it doesn't depend on the previous states or actions. And that's a way to say, imagine you're trying to learn how to drive a race car. And you could say, well, I'm at a particular point of the track, and if my fuel's low and I press the gas, I'm going to go faster. But if the fuel's high and I press the gas, vice versa, if it's low, I'm going to stop. That needs to be encoded in the state space, not in some external memory, like how long the car's been driving or something like that. No, that needs to be encoded in the state space. So essentially, this piece of track would have a different representation for the cars in it with low fuel, the cars in it with medium fuel, the cars in it with high fuel, the cars in it with full fuel, whatever the possible states are for your fuel level. And everything needs to be baked into the states and the transition, the state transition based on the actions, and et cetera, et cetera. No external memory. That's a Markov decision process. And so it can apply to many things. We'll see some examples of some toy things it applies to. And then, of course, advanced versions of the algorithms can break all of these assumptions and put you in environments that are a little bit more realistic. For today, let's stick with this. Little bit more vocabulary that is, among the confusions of getting into reinforcement learning. You're not learning a model. You're not trying to go from X to Y. You're learning a policy. That is, you're trying to go from the state the agent's in to the action that the agent's going to take in that state. And the policy for today's purposes will be represented as pi. So pi of s is the agent's policy across the entire state space. And you could give it any viable state, and this function will return the action that your agent will take from that state. And learning an optimal policy, a good policy, an acceptable policy, that's what we're about. Another way of saying that's what we're about, a little bit more technically, is to say that our goal is to maximize across all time, starting from the beginning of time going to infinity, this thing, don't think about that for a second, times the reward that the agent got at the time t of moving from the state that it moved from to the state that it was at to the state that it was moved from, where the action you select is based on your policy. So what you've just learned there. So you want to maximize the reward you get by following your policy over time with this factor, which essentially downweights things that are further in the future. I mean, I guess, you set it less than 1. That's an important thing to have. Some of the algorithms we're working with converge. But conceptually, you could say, back to that explore-exploit trade-off. Do you want the agent to get rewards that are way in the future? Or do you want the agent to just suck up as much rewards in its current location as possible and not worry about that? And this is something that you have to tune when doing reinforcement learning, tune it for your environment, for your application, for your goals. All right, there's the goal. Another important piece of terminology or an important concept to think about when you think about, well, what are we trying to do in reinforcement learning, is to estimate the value of having a particular policy in a particular state. And so you could reason about, well, what would my value be if I changed the policy? And in general, you'd want to find the policy that has the highest value across every possible state. So to think about the value of a policy in the state, you have this little expression on the right. Now let me break it down a couple different ways. The first thing you could look at is this initial part of it says the probability of moving to each state you can get to from S. Put another way, you sum over each state that you might end up at. This is something like you've picked the action according to your policy, and now you say, well, what's the probability of ending up in each of those states? So if you can get to S1 and S2 by taking action A from state S, S'1, S'2, and if this is 75% likely and this is 25% likely, you would see that the probability of moving to each state says that when you move, you have to attribute 75% of the value to the fact that you ended up in S1, but you also have to attribute 25% of the value to the fact that you might possibly end up in S2. Now let me do a little bit of an eraser thing here. So you kind of normalize across the states that you might end up in, and then you take the reward from making that move. So all you control is what action you take according to your policy. There's a little stochastic behavior in the environment. So because of that, you might end up at multiple different possible S primes. And then you essentially multiply the reward of ending up at each of those by the probability that you're going to end up at each of those based on your move. And then you add in let's click it so you can read it, the value of being in the state that you end up at. Here's the value of taking the move you take. Now you're in a new S prime. And so you do the discount. Remember, we talked about the discount of the value of ending up where you end up. This is just a way to say that, put it in another form of English, the value of being in a state is the value of the action you can take in that state plus the value of being in the state you end up in. If you can end up in a great state from the state you're in, then the state you're in is pretty darn good itself. And this is a way of thinking about that delayed reward, that your reward isn't just what happens locally. The reward is also where you end up. Okay, we're going to go through examples and examples and examples and examples. And let me get out of the way here. Now, everybody talks about a little robot game where you can have a state space. Here it's a 3x3 state space where the robot, but I had these animations from something I worked on. So you could be in any of these 9 states, do a little click. So this is location 0, 0. Right now, the agent is in location 0, 2 in this particular example. Those are the states. The actions are to move within the map. So the agent is able to, at state 0, 0, the actions available from state 0, 0 are to move east or to move south. Can't move north, can't move west. That's the end of the world. There's dragons there, whatever. But you have those actions. In state 1, 0, which is right there, now you have 3 moves possible. You can, so, and then in state 2, 0, that's a special state. There's no moves available because in this simulation, that's the reward state. So if the agent ever gets to that state, the experiment ends. The agent gets 100 reward, and there's really no other reward available in this environment. So the agent can walk around in circles for here forever, actually forever, and get 0 reward. But if the agent ever takes that step or ever takes that step, the agent's going to get some reward. Okay, well, this is the environment that I'm trying to set up so that we can demonstrate the first reinforcement learning algorithm that we're going to see and walk through concretely and see the examples. In practice, you would set up a different environment that's appropriate for what you're doing. Not everything has to be a robot. So there you go. PowerPoint animation, got his reward. Now back to policies. What does a policy look like? A policy, remember, is for every state, what action is the agent going to take when it finds itself in that particular state? Now, one piece of an agent's policy might say, when I find myself in state 0, 0, I take a step to the south. That's part of a policy. It's not a complete policy because you need to have a policy for the entire state space so you know what you do when you're there. In this case, let's say, well, if you get to this or this, you're going to take the east step. Let's just blast this through and add up the rest of this policy. When you're in the terminal state or this final state, you could say your action is nothing because there's no actions available. And then there's some more stuff. There's your policy. Now the question is, how good is this policy? And remember, we had this notation to talk about the value of being in a particular state, having a particular policy. Here's a particular policy. Let's say we're in a particular state. And you can remember that this is the rewards for getting to the chest. And so the value for having the policy that we happen to have and being in state 1, 0, remember we had the components of the reward we get for taking the action we're going to take and the discounted future reward for all the actions we're going to take downstream. Well, what I've drawn right here is the reward for taking the action we're going to take, which is we're in 1, 0. We look up in our policy, we're going to move east. We look up here and say, aha, we're going to get 100 reward. And, this is a little notation. Y to the 0 means there's no discount on this. So that's what we would say. For the immediate action, this is how you could represent its value. And that's kind of what we've drawn up here. But remember, we have to take the discount. So you would say the reward for taking the action that I would take in state 1, 1. Let's look up 1, 1. We're going to move north. So the reward that you get for taking that action is 0. And you don't discount it. Y to the 0th is 1. So you don't discount that reward. But then you take the next step according to your policy, and now you're discounting by whatever that parameter is the reward that you get for taking the action you're going to take there, which is still the same action, this move east. So you can see that the reward is less, and you can iterate this further and further and further back. This case, the value of being in state 0, 0 with the policy that we have on the slide is 0 for the first step, discounted 0 for the second step, even more discounted 0 for the third step, and highly discounted dump, 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 and then you take the final step and you finally get the reward. So the value of that is 12.5. I don't know if you noticed this, but I specified a value for that discount parameter of 50%. Now we're getting somewhere because we know how to move around. We know how to encode, well, here's what my agent's going to do. We know how to say this is how valuable having the plan that my agent has. What are we going to do next? We're going to realize that the policy could actually be better. And what does it mean to be better? Well, in this state, the policy goes there. Should just go there. That would be better. In this case, the policy goes there. Should just go there. That would be better. In this case, the value of your policy, maybe the action there is correct locally, is that you basically want to head directly towards the chest. But because then you hit this detour, the value of your policy isn't as high as it could be in that state as well. Now we have some of the concepts that are important to reinforcement learning. We're going to talk about an early, simple, the one we're going to implement, reinforcement learning algorithm, Q learning. Q learning, the goal is to learn a policy that optimizes the value of the policy for all states, no matter where you start. And you want to have no prior knowledge of the state transition probabilities of your Markov decision process, MDP. And you also want to have no prior knowledge of the reward function. Basically, come to environment, all you can know is what are the states, what actions can I take at the states, and go. Explore and come back when you have an optimal policy under, certain assumptions, which we will talk about. And the approach at a really high level is we need to learn something like a policy. We need to estimate, we need to find a policy that maximizes the value. Use this concept called a Q function, which is why it's called Q learning. So instead of learning a policy directly, what we do is we learn for every state and action combination, what is the estimated value for taking that action in that state. That's not a policy, that's a superset of a policy, but it's the superset that you need to learn in order to extract an optimal policy. The Q learning algorithm initializes an estimate of this value to 0. Starts off, it says, I don't know anything. Let's just assume there's no reward in the world. No matter what I do, it's pointless. Go in circles forever, get 0 reward, blah. But that's an initial estimate. Now we have to run the algorithm. So you repeat forever for a while, for as long as you want. You just take a random action from the state that the agent happens to find itself in. You receive S prime as always, but also you receive the reward that you got for that particular action ending up in that particular S prime. Now remember, it's stochastic, so you do the same thing again, you might get a different S prime. Then when you get the reward from the environment, you update your estimate. Remember this thing here. It starts off at 0, but as soon as you find some reward, you plug it in to your Q function. By updating for the state you were in and the action you took, the reward you got, the state that you ended up at, and then you add in the discounted reward of taking the best action in the state that you ended up in. I don't know why I ended up in that state. I don't know what action my policy is going to take, but if I select the one with the highest value, that will be my estimate of the future discount reward of ending up in that state. Don't worry, we're going to walk through examples of this with our little animated robot environment. We're going to do it 5 or 6 times. I don't know. This will all be very clear, but just one more time, we have this function for every state and action that you can take of what you're going to do there. You explore the environment, just kind of walking around at random or according to some, we'll talk about how you decide where to walk. Every time you find some reward, you update the reward of being in the state you were in and taking the action by the reward you got plus the future discounted value of taking the best action in the state you end up in. Okay, said it multiple times, maybe too many times. You can also, in order to get these algorithms to converge, you may have this alpha, which essentially what this says is based on the number of times you visited the state, you start to burn in what you've learned. That is, as that grows towards infinity, the amount that you trust the new things that you're finding goes down because this number will get smaller and smaller, and you start to just trust the function that you already had without updating it. This is an important thing to say, like the algorithm that I'm presenting to you is going to converge at the optimal if a bunch of things hold, and eventually you burn in what you've learned. If you don't burn it in, the algorithm isn't necessarily going to converge. Now, the exploration policy that you would use in this algorithm, I mean, I guess you can choose different things, but the simple version of this algorithm says this. Now, look at that for a second and tell me what that does. You should recognize this from the neural network architectures lecture, the structure of this math. So say it's a useful structure. It appears in multiple of the algorithms that we work with. And what this does is converts your Q hats for every action for the state that you're in into a sum across the states that sums up to 1. It's the same as the softmax. So you're able to turn the Q hat estimates that you have into essentially a probability so that you can take a random number from 0 to 1 and use that to choose where you're going. So apply a softmax, do that. And then if you're in a terminal state, like you found the chest in our example, you just do a random restart, put the agent somewhere else and let it explore from there. Then when you're done with this, you have a policy and it will be optimal if everything holds, if all your, you set up the environment and everything correctly. Eventually your policy is to look at your Q function that you learned and at every state, just pick the action that has the maximum value for that state. In essence, the Q function you're learning isn't just the best state, it's the value of all the states. And if you pick the best state, you have a policy and that will be an optimal policy. Let's go through some examples of that. And there's a lot of concepts floating around. I think when you see it concretely a couple times, it'll make sense. Now, here's the same environment we had before. Remember, we had the big green arrows, which were our policy for where to go from each state. Now we have these little gray arrows, which represents the estimate. This is the Q function, the estimate of the value of being in this state, walking west, will be stored on that arrow. There'll be a number there which says what is our current estimate of the value of taking that action from that state. So you initialize all of these to 0. Hopefully you can zoom in your screens a tiny little bit and see these. So at the beginning, our Q hat for every state action pair is 0. Now we get a random initial state, 1, 1. A random action from that state, move east. The environment gives us a reward of 0. We've updated this, remember, let's see if it comes up on the click. Yet we updated that to be 0. Why did we do that? Because the reward that we got for taking that action was 0. And then we can look at all of these, this one, this one, this one, they're all 0. Even though it's behind the guy, you can't see it. I'm sorry for that. Those are all 0. So when we update this part, you add your discount parameter times 0. Well, it's going to be a 0. And that's the update that you make for taking that move. Now you get another random action, and I didn't want to make it random because I want this to be faster. So you go up, you get this reward of 100. Now watch what's going to happen there to that particular element. We're going to update it to be 100. Why is it 100? Because the reward that we got for going to that place plus the discounted reward for the best action you can take from there, which is 0 because there's no actions you can take from there. And that's why we update this value of the Q function to be 100. All right, no more moves possible, start again. Now we still have this 100 set there from the first round. Now we're going to do the second round of interaction with the environment. So let's say that the agent starts at that spot totally randomly. We just got really lucky that I can show you this so quickly. So now we take that north, and we'll see that the reward that we get from going north is what? It's going to be 0. But now we have this. So on our previous round of exploration, we found a little bit of reward. We encoded it in this Q function. Now we step into the state from which we found that reward, and now we can percolate that reward back to where we came from. Say, hey, you know what? Guess what? If you're coming in this direction, you're on the right track. You're starting to bump into some downstream rewards. So we are going to take this and update it. 0 reward that it found, the discount, remember 0.5 was the parameter that I'm using in these examples, times the 100 reward you can get to from state 2, 1. So now we've updated that to be a 50. Then if you take another random action, you go there, you find the same 100 reward, you can re-update this. Remember, you could burn it in. I mean, over time you would trust the new observation versus the old observation. The more times you visited the state, you would trust the old observation more, right? Bake it in. No more moves possible, start again. You can continue doing this a lot of times. So now I'm going to just kind of draw a green arrow of the path that was taken and update the values of the Q function as they get encountered. Random initial state 0, 0. So it could take this path and look, it just updated the 50. Then it goes some more and now it updates the 25, goes some more. Now we can run this again, different place. Okay, now there's another update. The value is percolating back towards the beginning of the run. We could do it many times. I don't know how many times. There's randomness involved. It could take a lot of times. Large state space, it could take a really lot of time. But eventually, as you go through another random run, you'll find, hey, there's no updates to do to my Q function. And you do it again, there's no updates, there's no updates, there's no updates. Everything already has a value. And when it's converged, you've got your optimal policy. And again, the way you express that policy is that in any state that you're in, to find the action, you look at every possible action you could take. Those are all the ones leading out of that state. And you find the one that has the largest value. So in this case, there's two that are tied. So you break your tie somehow, and the policy for what to do in every state is encoded within this function that you've just learned and converged. Here you go. That's the policy. It's better than the policy we started out with because remember, these two things are both heading in that direction. This guy is heading in that direction. Everything else, there's choices. You could go up or you could go right. All right, so there you go. That's the algorithm. That's how you run it. It could take a while. When you're done, you're able to extract the policy that you want your agent to have. Now we're going to go through some challenges. When there are many states and many actions, it can be very hard to stumble upon that first reward. And it can be very hard to stumble on that reward again and to stumble on that reward again. These probabilities can get really tiny. So like to find the reward in the first place might be like 0.1%. To find that again might be 0.11%, something along those lines, because it's kind of percolating back. And to find it all 1,000 times you need to fill up the whole state space could take forever. It's a particular problem in a couple of scenarios. One is that there's time. Like let's say you do have fuel or you have a time limit. You might go through the game, or there's enemies that are going to kill you, something along those lines. In this case, the reward, you may never find reward. In order to get from that spot in the lower left to that chest in the upper right, you need to make like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15 something. I don't know. Like who wants to count? Each step has a 50% probability of going away from the reward. So even though it's not a confusing maze, a maze might actually be easier because it would restrict your choices. And in this case, you have 4 choices at most of the steps. I mean, anytime you step downwards, you're stepping away. You're doing the wrong thing. The timer's ticking. You're not going to find your reward. Anytime you step to the left, you're doing the wrong thing. The timer's ticking. You're not going to find your reward. And in this case, the probability of reaching the goal at all is 0.01%. So what does that mean? That means you run the agent interacting with the environment 100 times, you get 0 rewards. You run it 1,000 times, you get 0 rewards. You run it 10,000 times, and maybe you're starting to expect to get some rewards. So then you need to find it a bunch. So you're going to have to run it like 1 billion times. That's not good. Another thing is when there's a narrow path to success, and this was like the Montezuma's Revenge. This is just another example of it. If taking a step north or south from this spot ends the episode because you've died by falling off of the rope, this particular path becomes very hard to ever traverse. So you'll be pretty unlikely to find this reward in an amount of time that a human wants to spend running their reinforcement learning algorithm. In exploring randomly, 97% of the time, given this setup, you're not getting across the rope. That makes things even harder. There's a couple of challenges. One thing that is common for people to do, it's very seductive, is you could tell the agent, hey, the environment has this reward, but who cares? I don't know who made that environment. What if I give you some reward for making progress, for getting closer to the real reward? And that's called reward shaping. You're the person building the environment in many of these cases and coding your problem in a way for, yeah, this is what I want my agent to do. So you might just say like, look, crossing ropes, that's a good thing. I'll give you some reward for getting there. It might look something like this. You could say, well, hey, there's a little reward just for getting onto the rope so that you explore over here for a long time. So you found this reward, you get that for the first time, and remember the exploration policy to say that states that tended to have some reward, maybe I'll be a little bit more likely to head in that direction. So eventually the reward from that will percolate back to where you start. And then you're falling. Now you found this reward. That's good. It's heading you in the right direction. Eventually you'll learn like, hey, I'm, more or less better off to follow that rope. Get over there. Okay, reward shaping. That can really help. But now there's a human in the loop. Now you're essentially providing labels for intermediate states, which in this case, it can be obvious that that's the right thing to do. But in some of these more open-ended games, it's not obvious. One thing that is, if you follow the AlphaGo stuff at all, you'll see that as the machine got better, it's starting to play the game. It's starting to create structures that no human has ever created or played, or like master level humans wouldn't play. That's because it's sort of evolved beyond the meta game of what humans do to each other, and it's defending against different things that no human would. Anyway, so you are in many ways potentially crippling your algorithm by putting your thoughts into the environment. Here's an example of a boat racing game. I just thought it was pretty cool. So this boat is supposed to go around the track and win the race. Okay, so you can use reinforcement learning. You saw the other boats like zoop by there for a second. And it's supposed to be with those other boats. But the people who set up this environment didn't like that their boat wasn't picking up these speed boost rewards. So they did some reward shaping and they said, hey, you get 100 points for winning the race, but you get 5 points every time you pick up one of these speed boost rewards. And they learned an agent that drives in circles, picking up these reward shaped rewards, not achieving the goal it's supposed to achieve, and just drive in circles there forever. And its total reward, the total reward for this policy is gigantic compared to winning the race. It's an example of how reward shaping can fail. Now you would go in and be like, oh, okay, well, I said 5. Maybe I should say 2.5. Maybe it should be 1. But you kind of just get on this slippery slope where, what are you even doing? I mean, you might as well write a program at this point. If you're programming the agent's AI with the language you have of scattering rewards various places and then running a reinforcement learning algorithm, I don't know, maybe just write code. That was one problem and one approach. Reward shaping is a thing that people do. You probably have to do it if you get into these gigantic problems. Another thing that is obvious is you can use memory. That is, you maintain samples of the actions you took and the rewards that you got beyond the initial use of them to update your queue function. Do an exploration, you find some stuff. You did 2 updates, but now that you've done, for example, this update, it is clear that you could do the same exploration and also do an update there, and also do an update there, and also do an update there. Why aren't you doing it? Why are you gonna say, well, let's wait until the environment randomly walks me through those things before I just go and do those updates? I can just replay that episode over and over and over. Replay it as many times as you want, and you can get some initial estimates for the queue hat faster, percolated more towards the initial states. It can be fantastic. It kind of skews some stuff like the number of visits you do to each state. It's not totally random, but that probably doesn't matter too much. And just to show that you can keep a cache of multiple useful paths and like 1,000 that cover the state space pretty well. And every time you find a significant change, replay those 1,000. You can come up with all sorts of crazy policies for that. And it's a useful thing to do when the cost of running a simulator is a lot larger than the cost of replaying a path that you got from the simulator. If everything's in a computer, and if things are fully observable and you don't have to wait for any other agents to figure out what to do, just completely do the randomized simulations. But if, on the other hand, you're dealing with an actual robot that is actually stacking things, and each simulation involves like a 30-second robot arm doing thing, then use a memory. Don't make that slow simulation find rewards slowly over and over and over and over. And clearly, if it's hard to get rewards, the first time you find a reward after 10,000 times searching for it, percolate that thing back. You're gonna wanna do that. All right, that is that. There you go. Q learning, first algorithm, reinforcement learning. This is the assignment we're gonna do. We're gonna take a environment that somebody has built. It's an environment engine that lets you simulate many different reinforcement learning environments against many different reinforcement learning algorithms. It gives you a visualization of the state space, what's going on. The particular problem we're going to do is this cart pull one. And here's the thing is, you want to learn the policy for controlling the tray to balance something, on it. So you want to learn how to get that thing in balance. The reward is +1 per step that the pull remains up, that you remain in balance. And there's a time limit that you can get up to, I think it's 200 as your maximum score if you learn the policy to balance that pull perfectly. I think the state space starts with some small random torques on the pull. So there's a little bit of, I think the state space is the inertia, the position, something along those lines, the position of this and the position of that. And that's what you need to implement Q learning. Learn a policy, demonstrate that it works on that. Here's a tiny bit of the framework code just to walk through this and connect it to the assignment that you're going to have to do. There are instructions for how to install it, but you import Gym, then you create an environment. And so that's what your agent is going to interact with. Cart pull v0. There's a bunch of different environments. If you get into this stuff, you can just have a party there. Here's some import statements. Of course, there's going to be some preamble on these, but there's a framework code, Q learning, and Gym support. I think I did, this may change a little bit in the version of the framework that's online now, but I took the state space here, which is a continuous state space, and discretized it so we can use Q learning. And there's some parameters about how I did the discretization in these files, so you can see that. You can set that. Now you create your instance of Q learning with all the parameters that you want to pass to your algorithm, all the decay rates and all the different things. Then you go over the number of iterations that you want to go over. You reset the environment, so you put the agent in a new initial state with some randomization, probably to the location and the inertia that's on that pull. Then for the number of steps of that particular interaction with the environment, you render it to draw this picture. Like I say, comment that out if you don't want to draw the picture, because drawing the picture can be quite slow. Then you say, well, what's my current state? And this function is the one that I wrote that takes the initial observation, the observation of the initial state, and discretizes it, so we have a Markov decision process. Call your learner with the current state and whatever the parameters are to get the action. That will be based on whether you're in exploration mode or whether you are trying to use the optimal policy. So you'll have to put that into the code there somewhere. Old state, tell the environment, hey, take this action, and it knows what state you're in. And then you get the reward. You get a signal for, is the simulation done? Like, have you failed? Some extra info. Then you observe the action to update your Q function. Now, once you've done with learning mode, you could apply that policy, and you're going to need to do that to create the hand-in that you're going to create. Anyway, I felt like this was different enough from other things. I just wanted to show you the code along with the algorithm, and you guys are going to do fine. In summary, reinforcement learning, very popular, exciting, impactful technique. A lot of things you read about in the newspaper and you're like, holy cow, a computer did what? It's because combining reinforcement learning with like something deep networks, things along those lines. In reinforcement learning, the goal is to maximize the reward the agent gets over time by taking actions. The data you use to train or to learn your policy, instead of training a model, you're learning a policy, is that you're able to interact with the environment. Looks a little bit like this. The agent sends an action to the environment returns a new state and a reward. Many awesome recent successes: robotics, beating humans at difficult games, doing it with essentially no human knowledge. This is another area where there are breakthroughs happening every year. Interesting stuff. But there are a lot of challenges with getting reinforcement learning to work, and this notion of having completely knowledge-free reinforcement learning algorithms that can apply to any environment without a lot of work. I don't know, maybe, maybe not. It's hard to say if these recent successes involve tuning like the algorithm, the architecture of how the different parts of the system communicate, or are we really making progress towards a generic fire and forget reinforcement learning system that can learn any human problem? Specific challenges that I think you might bump into in simple reinforcement learning are when it's tough to get reward. Either there's a lot of ways it can be tough to get reward. The state space is too big, too many actions, lots of ways to get to terminal states that don't give you reward. It gets very, very difficult to learn a good policy. Remember, simple technique is Q learning, where you're trying to learn the policy, but instead you learn the complete combination of every state and action you can take. What's your expectation of the future discounted reward of doing that? In order to get this to converge, you might want to consider things like memory or a little bit of reward shaping and lots of hyperparameter tweaking and tuning to get to the right values. All right, well, that's Reinforcement Learning 101. Quick introduction to an exciting, deep, big topic. Hope you enjoyed it. Take care.